Okay students, let us try to solve another numerical. So the question is, what is the energy in joules required to shift the electron of hydrogen atom from first Bohr orbit to fifth Bohr orbit? And then what is the wavelength of the light emitted when the electron is returning to the ground state? And they've given you the ground state electron energy. Okay, so see, the question is, you are having first orbit, second orbit, third orbit, fourth and fifth orbit. Okay, so the question goes like, the electron is jumping from your first orbit to fifth orbit. Electron jumps, and what energy is required to shift this particular electron from first to fifth? That we need to first find out. Okay, so, and the thing which is given to you in the question is ground state electron energy is given to you. So ground state electron energy which is given to you is equal to minus 2.18 into 10 to the power of minus 11 ergs. So first and foremost thing, let us see that we are converting this ergs into joules. So we know the relation that 1 erg is equal to 10 to the power of minus 7 joules. So your minus 2.18 into 10 to the power of minus 11 ergs will be giving you minus 2.18 into 10 to the power of minus 11 into 10 to the power of minus 7. So you get back minus 2.18 into 10 to the power of minus 18 joules as your ground state energy. Fine. Now, next thing what we need to do is, we know the formula that En, that is energy of your nth level, is given to you as minus 2.18 into 10 to the power of minus 18 divided by n square, which is in joules. Now here the electron is jumping from first orbit to fifth orbit. Now how much energy is required to shift? So what we can do is, we can subtract the energy what it has on to the fifth level from what is the energy it had on the first level. So it can be solved like this. Delta E will be considered as E5 minus E1. This formula we can use. So now delta E what we are having is, as per the formula, minus 2.18 into 10 to the power of minus 18 joules, and as it is divided by n square, and you need to find out the difference between the two energy levels, and this is a constant value, so we can take it common. So the formula will be 1 by n2 square minus 1 by n1 square. So here we can proceed like this, minus 1 by 2.18 into 10 to the power of minus 18 joules, and here your n2 is the final level, that is your fifth level, so we can put 5 square, minus 1 by n1 is your initial level, so we can take there here 1 square. Solving this will give you the difference in the energy. So let us quickly solve. 2.18 into 10 to the power of minus 18 joules. This will become 1 by 25 minus 1, which gives you 24 divided by 25. But then here it would be minus 24, is because this would be 1 minus 25. So you can see that this minus terms which you are having, you can cancel them, and then you will get, multiply this particular 24 with 2.1418. So answer here you will get 52.32, and here you have 10 to the power of minus 18. Just note, it is not this minus which you are cancelling, it is this minus which you are cancelling. This is power. Okay, this one was power of 18. So when you multiply 24 with 2.18, you get back this. In the denominator you have 25. This is in joules. So answer what you get back here is 2.0928 into 10 to the power of minus 18 joules is the answer for change in energy. So that much energy is required for your electron to jump from your level 1 to level 2. Now if you will look at the next part of the question, it says that what is the wavelength of the light emitted when the electron returns to the ground state. So the electron which was here now has to return back. Now when it is returning back, what will be the wavelength? Fine. So utilizing this particular energy, it has excited. Now it will liberate this amount of energy only. So ground state, when it is returning, N1 will be 1 only. So now lambda you need to find out. So when electron returns to ground state. Okay. Now we are aware with the formula, delta E is equal to hc by lambda. Now from here we can see that we are knowing the value of h, which is Planck's constant. It is 6.626 into 10 to the power of minus 34 joule sec. Also we are aware with the velocity value of light, that is c, represented as, value is 3.0 into 10 to the power of 8 meter per second. Now as we are to find out the value of lambda, let us write it as lambda is equal to hc divided by delta E. Let us put the value and try to solve it. 10 to the power of minus 34 joule sec into 3 into 10 to the power of 8 meter per second divided by the value of energy which we got was this one. This is the value which we got. Let us put here, that is 2.0928 into 10 to the power of minus 18 joules. Here we can cancel this joules and joules. Also we can cancel this per second. So the answer which you will be getting would be in your meters. So now when you multiply 6.626 into 3, you will get 19.878. Then you divide that by 2.0928 into, now this particular 10 powers which you are having can be written as 10 to the power of minus 34. Then this is in the denominator, will be taken up, will be plus 18, and already 10 to the power of 8 you are having. So it can be written like this. Upon solving this, the value of lambda you get back is 9.497 into, you can see it is 34 and this will be 26. So this you will get back 10 to the power of minus 8 meters. Or what you can do is, you can just shift this decimal point. You can just shift this decimal point here. So answer what you will be getting for lambda can be written as 94.97 into 10 to the power of minus 9 meters. And here lambda can be written therefore as approximately 95 nanometers, since you are aware 1 nanometer is equal to 10 to the power of minus 9 meters. So this is the wavelength of the light which will be emitted into the, when electron is coming to the ground state. So you can just have a look at the numerical which will be solved this particular way. I hope you understood. Thank you all.